theoretical definition of what path loss does. Path loss is actually proportional to the square of frequency. So what this means basically is as we start going up in frequency, the amount of path loss that will be encountered by a wave in propagating in free space increases quite drastically. So by the time I am in the 10 gigahertz plus type of spectrum, my path loss increases by almost 20 dB compared to 6 gigahertz or lower. So in order to compensate for this huge loss in the signal strength as the wave propagates in free space, we need to increase the gain of the antenna, which would be the logical step. Now, like with everything, there is a trade-off here. As I pump in more gain in a particular direction, the pattern becomes more directional and the beam becomes narrower. So that means my beam width, or which is the direction in which the beam points, becomes narrower and narrower. So I have to deal with scanning requirements. One more thing to look at is the antenna size and how this works. So in this particular graph, on the y-axis we have the antenna gain in dBi, and on the x-axis we have the area of antenna in millimeter square. For example, let's take an example of something that is 5 centimeters by 2 centimeters, 50 millimeters by 20 millimeters, which will bring me to 1000 millimeters square on the graph. So at that type of surface area, if I'm looking at 0.8 gigahertz, 0.8, 1.9, so we're looking at the typical LTE bands, sub 6 gigahertz, and the orange curve is at 28 gigahertz. So at that 1000 millimeters square, the gain for just the normal antenna structure, we are not taking into account other factors like reflections from the PCB and other things that we can do to boost the gain of the antenna, will be around minus 10 dBi. At 0.8. At 1.9 gigahertz, that gain goes up to minus 3, minus 2 dBi. At the same time, for a similar size antenna at 28 gigahertz, that gain is going to be 20 dBi. So, good thing that we get the gain up, but what we have at the lower frequencies where the pattern tends to be more omnidirectional, where you don't have to worry about scanning requirements or where I don't have to worry about where my receiver is with respect to the transmitter. Those kind of things become very critical once I have gain which is that high. And just to give you the mathematical relationship of how 3 dB beamwidth is something that we'll talk about a lot. 3 dB beamwidth is basically just the roll-off where the gain of the radiation pattern drops by 3 dB compared to the peak gain. And how wide is this beam? So the 3 dB beamwidth in this particular case, again the x-axis is the aperture length in millimeter. In this particular case, we can assume, let's assume a patch antenna, rectangular patch, x and y dimensions, Lx and Ly. The 3 dB beamwidth can be just given by the simple equation on the screen. What happens here is as the beamwidth, as the gain of the antenna actually increases, your beamwidth starts to narrow. So when we start with a very small antenna, the pattern tends to be more omnidirectional, you have a lot of beamwidth. Now as we start pumping up the gain, similar to what we saw from the earlier phase transmission formula and other examples at 28 gigahertz, if we are looking at 20 dB, 23 dB or even higher type of peak gains, a 3 dB beamwidth is going to start to become very, very narrow. And you see the threshold. It kinds of the role, the intersection point right now is where the beamwidth is under 20 dB in the teens, and it just continues to drop eventually till you are down to maybe a 3 dBi beam. Now, in addition to path loss, which is a multiplicative noise source as the signal propagates to free space, we also have to deal with atmospheric attenuation. And this particular graph is just simple analysis, kind of at room temperature, 20 degrees Celsius, sea level, and we are plotting it versus log frequency here. So what we see, what are highlighted on the graph there are the 28 gigahertz, 39 gigahertz, and 64 to 71 gigahertz band. You can see free space attenuation in this case can be 0.2 to 0.3 dB per meter as we move forward. It can be significantly higher at the higher frequencies, which is 60 gigahertz or more than that. In addition to that, that is ideal condition where you are pretty much in ideal 20 degrees Celsius. Weather is perfectly fine. If you have rain, so this graph here is just showing rain conditions where it's tracking from kind of a very light rain going up to heavy rainfall, and what happens to the atmospheric attenuation in that particular case. And we see just for a medium rain kind of scenario at 28 gigahertz, your attenuation can be 3 dB per kilometer. So you're losing a lot as the beam needs to travel or propagate at 28 gigahertz. Similar models and studies have been done for indoor propagation. This was a few years back. New York NYU Polytechnic School of Engineering did a pretty exhaustive study. I think it's about a couple of years of research work at 28 gigahertz and 73 gigahertz, characterizing indoor propagation models of what happens. So in this particular case, what they've done is they have put different transmitters across an office building and an office environment, and they have several receivers. So there are about 43 transmit and receive chain combinations here that they're looking at. And what they're plotting here is as a function of separation in meters between the transmitter and the receiver, you're looking at path loss and dB. So in this particular case, you can see the best case when you both have both the transmitter and receiver line of sight pointing towards each other without any losses. The best case scenario, you have the green line there, which is kind of showing your free space line of sight path loss component. And the other components that you see here that are kind of going up and down is basically they had these two antennas sitting on turntables. So that is just to characterize what happens as the transmitter and receiver are kind of out of sync and the angle of arrival and angle of departure are not synchronized. In this particular case, you can see the path loss even at a given distance can fluctuate quite a lot. So this is at 28 gigahertz. They took this a step further. They also did the analysis at 73 gigahertz. So what we see on these two plots is on the path loss model, they just used a 1 meter free space path loss model. At 73 gigahertz, as expected, the path loss is much more compared to 28 gigahertz. And at 28 gigahertz, kind of this free space path loss component is around 1.1. Then you also have a shadowing factor, which is going to be 1.7 dB that we have to deal with as the wave propagates to free space. Now next, what we'll look at is some of the fundamental antenna concepts of millimeter waves. And to be fair, this is not new. The antenna systems at millimeter waves have been around for a very, very long time. They have been used in different industries, including defense and Air Force in the past. What we look at are three of the basic techniques that are used at millimeter waves. You have your traditional fixed arrays, which is going to be a passive antenna array. The second thing where you add a bit of adaptability to it is designing a phased array, where you can adjust the phase and scan the beam of a given array. And the third one that we'll look at, which is attractive for what we have been trying to do with 5G, is kind of adaptive arrays, wherein we look at some features like digital beamforming, and wherein the array becomes more digital than just being a standard analog type of array. So just to explain the three concepts, fixed array, this is passive antenna, a basic array, one-dimensional or two-dimensional. One-dimensional in this case means a linear array where you just have multiple antenna components offset by a fraction of wavelength in the same dimension. 2D array is X and Y where you have two components of the array. You have a fixed beamwidth, typically high gain antenna pattern. In this particular case, it can be used for fixed applications wherein you don't expect any type of attenuation or reflections to the signal. The transmitter points towards the receiver and you have line of sight communication. Phased array, which is something that could be considered 1D or 2D array again. In this case, you start with the fixed array gain or the pattern of the array, and then we can add phase offset on each path and we can start scanning the array pattern. and this can be done on both sides, and there can be a synchronization that can be associated on the transmitter and receiver so that they can scan and kind of track each other. Now, the last thing that I want to talk about in terms of the array design is the adaptive array. And this becomes more interesting because this is where we add in a bit of signal processing at the feed of the antennas of the array. So in this case, instead of starting with a pattern which is predetermined or fixed, what we can do is we can kind of have some kind of a feedback loop with the baseband, which will allow us to kind of manipulate the shape of the beam, which is kind of what we do in beam forming, where we'll have some phase coefficients that can be added in on each of the antenna elements in the array, and we can shape the beam in a particular direction. And something that could be pretty useful when we are doing kind of a base station to a mobile UE type of scenario. Going into a bit more detail of what I covered, fixed gain arrays, just an example, line of sight